Bangalore, everywhere is Indiavadi.
Everywhere is India.
That's a nice one.
Yeah.
But the dust is quite high.
In both.
Yeah. Also, I didn't realize this Baner has become this massive
Crazy.
construction area. And just,
Everywhere, not
yeah.
just Banner. I mean, so anywhere metro is going with increased FSI and stuff like that, massive construction going
Yeah,
on
this
everywhere.
Kalyan Nagar is unrecognizable from
Yeah,
what it was and
yeah,
what
yeah,
it is now.
totally.
Yeah, I didn't take the metro because I think I had no mind space. We were just running from one meeting to another. So next time let's see. And I don't even know if on the routes you were taking the metro would have really made sense.
Yeah. No, metro is, yeah, it's tricky. And only if you can have a direct
Line.
metro, right?
Yeah.
Line. Only then it's okay. Otherwise, you end up spending more time.
Yeah. Yeah, it was faster with the cabs and the autos. So we have to go from like one place to another. Yeah, I went and checked MCCIA, but it's become very old now.
Where?
MCCIA, because I was thinking that we most of the
Mountain box
content
now.
is old and uses these as old school.
So where are you now?
I'm thinking of asking Nutanix to let us post it in the office because it's actually much nicer. The facilities are there, everything is there, and sleeping is there. So that's one option. Then some people told me about this office pattern in Pune, Kalyan Nagar. The pattern seems almost like an amphitheater.
Oh, is
Like
it?
it's literally an amphitheater. I don't know how people work in this office because it's almost like you like dump 200 people who are sitting next to each other and just working. So I went to the office and said, yeah, it's lovely, but it's not suitable because the moment somebody decides to leave, they can't be inconspicuous. Oh, this person is leaving and they're leaving from here. So I said, no thanks, I'll prefer a place where there is some multiple exits that you can enter. And then I visited the ThoughtWorks office, so Sarang said, think about it. So I said, I'll speak to Darshana and see what the capacity is.
Autos office, tricky.
Okay.
The where the challenges are now. I mean, previously it was all office centered. Right? I mean, there was a GM, general manager for office, and most of the things were decided by office. Now what they've done is make all leadership centralized. So office level, there are only admins in the sense like the people who do like day-to-day
Yeah, yeah,
stuff. But I mean, even I don't know who to ask
yeah.
to manage for something.
Yeah.
It becomes very tricky.
Because in Hyderabad it was quite crazy
Yeah.
because it's completely under the building management.
Ah.
So they have this OTP system of
Oh,
entry and
okay.
take a badge and leave. Yeah, they have the OTP system of entry and literally you can see the Hasgeek website on the night of 31st November everybody messaging. There is a OTP. I said that is coming from Raj Pushpa.
Yeah,
One
and Pune
point.
ThoughtWorks, they also gave away. So we had like two floors,
Yeah.
fourth and sixth.
Ah.
But after the pandemic,
It's
now that fourth floor is gone.
oh, okay.
So we only have one floor.
Yeah, Sarang suggested saying think of doing the workshops here. So I said that's
Yeah.
an option and in Savaj also they also I think literally it's pretty much the same neighborhood. So
Yeah, workshops is manageable.
I said let me check with Nutanix. I mean the unfortunate part of Nutanix is that those people require you to send your ID documents to generate
Oh.
this thing. So we said we are not sending any IDs by email. So they're like what are you hiding?
All the participants.
No, so just my colleague and I had gone to visit. So we
Okay.
have to send your PAN card and the Aadhaar on email. So
On email.
I said, this is a private document. So the immediate response is, what are you hiding? So we're hiding nothing. We're saying that we don't trust you with our data. So about it's a 3:30.
3:30.
We kind of wrapped up.
3:34.
No, no.
10.
We started at 10 in the morning. Yeah.
Yeah, so I'm now very tired.
I can imagine.
And we all come.
I was surprised you have like back-to-back events because all day workshop and then.
So I will probably just ask everyone to speak and we have conversation.
Is anyone from the workshop still here?
Some of them,
There are few
Satish is here. And a couple of other folks. Come sit, sit, sit. Please check the Anirudh is always busy.
Yeah.
Oh, workshop also. Yeah.
Please occupy the front seats. They are for free. They are not paid seats.
So, hi
Okay,
everyone,
you can come
welcome
here.
to Six Data. So
Front,
there's
the front row is free.
gents washroom there, the ladies there. There's tea and coffee behind. Please help yourselves. We have lots of snacks also arranged for you all. So don't feel shy.
Yeah, just make sure you don't dump anything on the camera. Okay, we just need a couple more minutes to start, but we really promised to. Then if people want to help themselves to coffee, they can get some and start.
This camera will be tracking.
Hopefully, for now, it is decided to track the wall.
Okay. Yeah, let it track.
Okay, I think in the interest of the early, the people who are here, we'll start the meetup. We were waiting for Anirudh Rauji from Bangalore Systems to come here, but maybe he can give the closing note. And Unmesh has had a long day, so Unmesh, this is over to you and to the audience.
Okay. Okay, so I'm very tired. I'm just, that's a disclaimer. So I would like to keep it more conversational than me talking about things. Maybe we'll refer to some code and while we are discussing certain topic. Yeah, I just have some code in there. I'm not going to talk about that code. But we are going to talk about data management at scale, right? So yeah, I mean, you can. What do you expect me to talk about when it comes to data management at scale? And why do you think data management at scale has challenges? No.
I mean, challenges, one I can think of is it involves distributed systems. One reason.
Yeah.
I mean, scale means usually you horizontally scale, so distributed systems comes into play, and that is a hard one.
That is a hard topic. Yes.
And because you need reliability also.
Reliability. Okay. Yeah, interesting. I mean, distributed systems, as you mentioned, is a hard topic, and you said you require reliability. Now, distributed systems is a hard topic, and there are reasons for that. Why it's a hard topic. One of the big reasons is that distributed systems need to work with failures as part of your system design. So for example, and that becomes very challenging with data, because imagine you have let's say a 3-node cluster, just to take an example, and one of them is constantly going to be down. Any one of them, let's say. And sometimes, the challenge starts from the figuring out that whether the node is down or it's just partially disconnected, right? Because how do you know if a node is down or something is down? There is no way to know, right? So what do you think? How can we figure out if you are running a process, like you are a process and I am a process, and I need to figure out that you are down. What is the way to do that? What do you mean by heartbeat?
We keep sending each other some message at regular interval,
Okay.
and then figure out if you're up or not.
Yeah. So if you don't send me a message in, let's say, 5 seconds, I consider you as down. But the challenge is that you might not be down. It's only that I am not receiving messages from you. And that's a very tricky challenge, right? Because if, let's say, we all form a cluster, and it's only that I am not receiving messages from you, but you are able to talk to everyone else. And I say that no, is down. And then based on that knowledge, if someone takes a decision, that you take a decision that, okay, move all the data that we were sending to this guy to someone else. But you still are receiving other requests and responding to them, then it becomes a challenge, right? And that's just one of the challenges of distributed systems, of partial failures. Partial failures in the sense that part of the system is unable to talk to each other, but part of the system is able to talk. And the challenge then becomes is twofold. One, how to make everyone else agree on the fact that you are down. And if you started taking some decisions, like if someone is writing data to you, and you start responding to that person saying, okay, data successfully written, how to protect against that and stop you from taking those kind of decisions. And two, or I should say one very common technique that's used is that of quorum intersection. So before taking any decision, that and when I say decision, something that you make visible to clients, because only if you are making something visible to client, only then all this consistency and other things that matter. If no one is reading your data, nothing matters. So that quorum intersection is a very, very interesting piece.
Sorry, Unmesh,
So have you heard of concept of quorums in general? Someone wants to talk about it, because it's a meetup. I'm not giving talk, so I'm taking this freedom to. So have you used quorum systems in your projects? Any one of you? So what distributed system products you use in your work, day-to-day work? Oh, you use Cassandra? Oh, 10 years ago. Okay. Yeah, because Cassandra has some very interesting failure modes that a lot of other distributed systems they don't have. MongoDB, yeah. Yeah. Zookeeper, yes. So there is a difference between the category of products which are like Zookeeper, etcd, or recent Kafka has this Kraft implementation, and CouchDB, yeah. And likes of Cassandra and MongoDB. And the difference is that products like, I mean, they all use quorum or quorum intersection as the basis of decision making. And decision, when I say making something visible to client. But products like Zookeeper and etcd, they implement something called as consensus, which is, and consensus also uses quorum. Quorum, when I say the talk to majority, I mean, roughly speaking, quorum is generally majority quorum, talk to majority of the nodes. But consensus adds some additional steps on top of basic quorum, because basic quorum, and maybe I think I should show some code. Yeah, I think I had some interesting. Okay, I will share this code base. But are you aware of the book called Designing Data Intensive Applications? I think that's the book that you go to if you want to learn distributed systems, right? And it actually documents some very interesting scenarios, and when it talks about consistency and consensus, that's the chapter it has. Now, consistency, when you talk about, in again very layman terms, it's the guarantee that you give to your users when they read some piece of data, what data is made visible to them, or what data is visible to them. That's the consistency guarantee. And if you guarantee that two different users reading one after the other, if first user sees some data, or some data is made visible to first user, the next user, like I read something and after 5 seconds you read something, you are guaranteed to get exactly the same values that I saw, or something that's written later. Now this is very basic expectation that we have, right? Now, when we use quorum kind of systems, quorum systems which only implement get and set, like what Cassandra does, or most of the NoSQL databases do, this basic guarantee is not possible to give. Like I read something, and after some time you read something, but you will get older value, and I get latest value. Because and this is the very interesting scenario from designing data intensive applications, and we'll use this scenario maybe to talk about concepts of linearizability and serializability. Have you heard of these terms, linearizable and serializable? And have you heard of framework called Jepson testing framework? Okay. So we'll see this thing. So what this scenario talks about is, let's say there are 3 replicas, and which are storing just simple values like x equal to 1, x equal to 0, etc. And there is some writer which is relying on quorum to call some write as successful or not. And the kind of interleaving of reads and writes that happen is like this writer goes to replica 3 to set x equal to 1, gets a successful response back. Now that writer has not yet marked that write as successful, but replica 3 now has this latest value. Now before that writer is able to send that value to the remaining 2 replicas, there are 2 readers who are reading that value of x, and the first reader, Alice, happens to go to replica 3 and replica 2, and Alice can read now value equal to 1,
Alice cannot reach replica 1 because of some network disconnection or network problem, right? And now this user Bob, you can see that it's all these messages there, that it's all happening sequentially, one after the other, right? Let's say there is some global clock and all this happening sequentially. And Bob goes to replica 1 and replica 2 but cannot reach replica 3. So you see that Alice read values before Bob did, right? It's sequential. And Alice could get value 1, but Bob got value as 0, right? Even when everyone in the system is using quorum, right? So writer is waiting for quorum of replicas to respond. So it's not marking that value as successfully written. Alice is using quorum for read, so it's it's responding, or it's marking that read as successful only after getting response from 2 out of 3 replicas. And Bob is doing the same, but it still cannot achieve this basic consistency guarantee that if I read after you, I should get at least as latest value as what you did. And why this happens is because of basic limitation of quorum systems, and this is one of the things I'm just highlighting, that why distributed systems are hard. And that fundamental limitation of quorum systems is that of ambiguity that they always face. Because when we say that we use quorum, we take any decision if we can get response from majority, like 2 out of 3, right? Or 3 out of 5, right? And what that means is that we never ever get full view of the cluster. So if, for example, Alice could get response from all 3 replicas, Alice could figure out that the value 1 that was returned is actually not copied to all the replicas. And then this is a scenario of partial write, right? The write is partial, it should not be exposed. But because quorum based system need to take decision only when they get they get responses from majority, they need to deal with this ambiguous situation where when they get some value from at least one of the nodes, they need to assume that this was probably successfully written by some writer, and it's just Alice or me that I'm unable to talk to replica 1, so I err on the side of assumption that this was probably a successfully written value. And this is one of the major reasons why you need consensus algorithms. Because consensus algorithms, what they do is that they don't take decisions immediately after they read a value from one of the replicas. They have additional steps to make sure that covers the scenario of partial writes. You're getting it? So at this point, the problem is because the values are immediately returned to the user, right? So even when we know that there is possibly this ambiguity that exists, that this is a partially returned value, it's immediately returned to the user. That is the problem. If you don't return it immediately to the user, then it's not a problem. And that is the reason, you might have heard of this CAP theorem, right? So any implementation that you need to do for achieving stronger and stronger consistency needs to handle this kind of situations and do more communication, or need to wait for more decision making to be done by talking to other servers again. And you can imagine that if you need to wait when you hit this kind of situation before you respond to the user, it naturally limits your availability, right? You will have highest availability if you just talk to one of the nodes and return to the user whatever you see. Highest availability, right? So even if like 1 out of 3 nodes is available, you will return some or the other value to the user, but user will always get some value. On the other hand, if you need to protect users against this kind of situation where you just don't return the value unless you are absolutely sure that anyone else trying to read the value or do anything with that value is guaranteed to get this value, then you need to do some additional to and fro, and it will limit your availability, because if you can't make a decision, you don't respond to client. That's the crux of consensus algorithms. If you cannot enforce a decision on the cluster, you do not respond to the client. And it is critical because, I mean, the example that we are seeing is just getting and setting of a value. That's some of the simplest thing that you can implement in a cluster. But products like Zookeeper or etcd or other products which are used for cluster coordination, they have more complex requests that they need to handle. Requests like register a lease or hold a lock, and that replica 1, replica 2, replica 3, they need to then coordinate amongst themselves to make sure that lock is actually held, and 2 different users trying to see if the lock is held, talking to 2 different servers, should not both get that lock. Now there are so many terms which are confusing about consistency. I mean, linearizability is one such, and if you go to Jepson's website, there is definition of so many terms, and one of the source of confusions or why there are so many terms is that there are some terms used by hardware community, because the same problems that what we just talked about, imagine this to be if you have a multi-core processor and each core like replica 1, replica 2, replica 3, you replace that with your processor cores, each maintaining on-chip cache, and your program setting some variable, and another thread may be reading it from a copy that's in another processor's local cache. You see the same problem, right? And for fixing those problems, there are protocols which work at the processor level, and or the interface between your processor and main memory. And that community has certain terminology for defining and describing scenarios like this and how to handle it. There is database community. So imagine this to be replicas of your database, and get and set are part of 2 different transactions. So databases generally talk in terms of transactions, and they also need to solve same problem, like 2 transactions going on, one write, one read, intermediate writes from uncommitted transactions. Do you make them available to the read transactions, right? There are isolation levels in databases. And then there is this distributed systems community, which is neither a database community not a hardware community, but they have their own terminology, and that's what makes understanding about consistency and consensus, particularly about consistency, so much confusing. Different communities talk about, I mean, they use different terms, almost meaning the same things. So this Jepson framework now, if some database claims like MongoDB that we use quorum based consistency, and that means we give you strong consistency, or they say we give you tunable consistency. Now, how to prove that the claim that they make is actually correct, right? And that's one of the reasons Jepson framework was written, to actually test products who claim that they provide certain consistency guarantees. And because this consistency world is so much confusing, can you actually programmatically prove that if I run this particular scenario, like this particular scenario, and there is a consistency guarantee, for example, called linearizability, which is the strongest consistency guarantee, can I prove by running a program and a test, particularly for this scenario, and prove that, okay, this is linearizable system, or what you claim in your marketing documents, is it actually true? Now, how that's done, and I will quickly demonstrate a framework. So I wrote a small framework for building distributed systems and then testing them. So as you know, I wrote this book called Patterns of Distributed Systems a couple of years back, and one of the reasons for collecting those patterns, I mean, it's just a side effect that it became a book, but one of the primary motives for collecting those patterns was that a lot of systems which come under this umbrella of distributed systems, and that includes products like Kubernetes, which are container orchestrators, or object stores like Amazon S3, or any distributed database like Cassandra or MongoDB, or products like Zookeeper or etcd, or message brokers like Kafka. There are so many products out there. They all have very similar looking building blocks because they come under this umbrella of distributed systems. And if you know those common building blocks, and what I have in this framework is actually codified some of those common building blocks, then it's very easy to, I mean, okay, I shouldn't say very easy, but it's relatively easy to try and understand what's happening at the code level. So when I say, for example, that let's say etcd uses raft consensus algorithm, how do I understand that when etcd says that it uses raft consensus algorithm at code level? I mean, if code is written in a general purpose programming language like Java or C++ or Golang, and it's the same language that you and me use for writing the software that we write, right? So this very tricky concept called consensus, if I have to implement in a programming language like Java or Golang, how does that look? And it's if you can do that yourself, it's a great way to learn about these complex looking concepts, right? And that was the reason I wrote this framework based on a set of patterns that we documented. Now I won't go in depth of that particular concept, but I know there is a session happening next week by Tiger Beetle folks. And Tiger Beetle, if you know, is a very interesting database. It's a financial database, but they use an implementation technique and testing technique called deterministic simulation testing. And this deterministic simulation testing is very interesting, because one of the trickiest things in network software. So when you have like multiple components talking to each other over network and working in a multi-threaded environment on multi-core systems, it becomes very tricky sometimes to reproduce. I mean, if in certain situations something fails, it becomes extremely tricky to reproduce that particular bug and follow or execute exactly the same sequence of events that a particular process went through to reproduce that bug. And what deterministic simulation testing allows you to do is it can reproduce exactly the same steps that a cluster went through, and it allows you then to exactly see what the problem is. But the way I use it in my example code basis is that I mean, one way is you reproduce a bug by replaying a set of events, but you can actually very deterministically take your cluster step by step into a scenario that you want to actually test or highlight, like this particular scenario. Now what this scenario says is that there are reads and writes happening, but there are tricky network conditions, maybe that messages are getting delayed or interleaved in such a way that writes from that writer are delayed and reads from these two users, they are actually reaching the servers ahead of writes, right? Even when you can see that writer actually started writing much before any one of these two started reading. And it can happen if, let's say, the writer has a network buffer which is flooded, or something, it went under a garbage collection pause. It can very well happen like that. Now, if you can introduce that kind of a scenario, that messages from writer 1 are delayed, and these messages are should go ahead of the others. Yeah, so you can see in this framework you can do something like this, that you delay a type of message from one node to a set of other nodes. And one thing that I should have noted is that you create a cluster so your entire cluster is embedded in this unit test. So right now we are running a 3-node cluster and you can name your cluster nodes, which are named as Athens, Byzantium, and Cyrene, which are Greek city names. I mean, just as a nod to Leslie Lamport, Leslie Lamport's original Paxos paper, he used Greek Parliament as an example. So this is like a 3-node cluster of this quorum replica implementation, and we are introducing a delay like this. And then you can, the advantage that you get by running a cluster all embedded is that you can inspect cluster state. Like you can actually, because the nodes in your cluster are actually objects that you can access within your test. So you can inspect internals of those objects and you can assert on those. then you can introduce things like you partition specific set of nodes. That means messages from a particular node will never reach another node. And then it allows you to actually, when you read, let's say, DDIA book and a scenario like this, you can actually code that scenario very easily and actually inspect the state of different nodes to confirm that okay, whatever is written in the book is actually happening.
One question. This runs like in-memory local, right? I mean, this itself is not subject to any of those errors. This is just single process in-memory.
This is single process, but the nodes themselves, I mean, if you see the quorum replica implementation rate.
I mean, I'm saying if this has bugs, then you are really not.
No. So let me. So this particular implementation, this is not aware of the fact that this test is running in memory. This will, so even if you run this as a main method, a different process working on a real network, exact same code will run the same way it runs in your test. And what you are doing is we are essentially, so when I'll just show you when this sends a message.
So it's an actual message, not simply updating a memory.
No. So they are not talking to each other. They are all I mean, all the nodes are talking to each other with message passing through a network layer. In the test, that network layer is simulated.
So in the actual implementation of the quorum KB replica, you use interfaces to mock everything up?
Yes. So yeah, I'll probably show you. So this, if you can see, when you send any message to a particular node there, it broadcasts it to all the replicas, including itself. Some internal coordination that's happening. And that broadcast is essentially sending this on this thing called as message bus, which is abstracted. And this message bus in your test, it will be using a simulated network. So this network, if you see, has
Is it like mini-net, something like that?
no, it's my own implementation. So it has it's a real network implementation. It has real network implementation and a simulated network implementation. And simulated network implementation allows you to have all these delays and stuff like that. But the beauty is that the same code that runs in your production setup with real network, that's getting tested in your test. So you are not so you don't have to actually know that I'm part of a in-memory cluster or I'm part of a remote cluster talking over the network.
So you've got mock versions of port acquisition and stuff as well?
No, simulated network is not using network at all. So it's just passing messages on the message bus instance, which is all in memory. But the NIO network that I have, it's the real network. I mean, so you will run those as like separate processes, assigning them IP address and port.
Exact same code you can know that is.
Exact same code you can, and this is derived from Tiger Beetle and Foundation DB. Foundation DB was the first one. But other interesting thing is this is also integrated with, as I said, Jepsen testing framework. And the way Jepsen verifies certain consistency guarantees is that whenever Jepsen clients talk to a cluster like this, so you can see that each client is named, and they are right now running in the same process. So it's guaranteed that this sequence of reads and writes we are controlling. I mean, we are doing it ourselves. But what it, based on the responses it gets each of these clients. Whenever a client gets a response, the clients maintain a shared history of events, and you can see that there is a client called writer. It invoked a write request, and it got a response back for x equal to 0. Then there is a writer that invoked x equal to 1, and this has not yet completed. So this is a pending write request. Now in between there is a read request invoked by Alice, and it got a successful response x equal to 1. After that, Bob invoked a read request and got x equal to 0. And after all this happened, this pending write request that was there, that returned and says that x equal to 1 is a successful write. Now Jepson testing, whenever Jepson tests databases like MongoDB or any, if you see Jepson repository, practically every database in the world is tested with Jepson, and Jepson repository has tests for all those. But to run Jepson, what you need to do is actually set up a cluster of those products and then use Jepson tools to introduce failures and run clients. And then it will give you a history like this, which you can pass through Jepson verifiers. Now what this deterministic simulation approach allows you to do is, even without setting up a real cluster, one good thing about Jepson framework is that it's a closure code and it's a closure library. So any JVM implementation can just use it as any other library, and that's the beauty of it. So what I could do is with the deterministic simulated cluster could get a history that could be fed to Jepson verifiers. And Jepson essentially allows, it tells you that if you pass it a history, it tells you if this is linearizable or not. And linearizable in simple terms is that if some client sees some results or some values, it should be a global thing. Anyone reading or seeing any results after that should see exactly the same value or a later written value, and that's a very rough definition. But you can assert that okay, this history is not linearizable, and this solves one of the challenges, particularly when reading about multi-threading or multiprocessor or distributed system books, is that you can now actually write code, and these concepts like linearizability and history and sequential consistency, you can actually see how it looks in code. So linearizability guarantee that people talk about. Now if I think I do have code for Raft as well, but if you can, let's say, implement a Raft consensus algorithm and generate exactly, the history will be better history, actual linearizable history, then you can see the difference, right? That basic quorum produces this kind of a history, and you test it with Jepson and it gives you failures. But with Raft consensus algorithm, you can actually see a linearizable history, and that probably helps you understand these concepts a little better. So yeah, I encourage you to try out this framework. This is all on my GitHub anyway. So I will stop talking now. I said I am not going to talk, but talked a lot. So any questions, anyone? Yeah.
How does assert eventually work? You just wait for the callback to finish up.
Oh, okay, that's an interesting thing. Yeah. So one of the key aspects of this design, it's all asynchronous and event driven, because we are essentially running everything in single thread. So each individual node executes everything in a single threaded execution chain. So any IO, whether it's a disk IO or network IO, has to be asynchronous. So for network it uses non-blocking IO, and for storage it uses async IO. And yeah, so the implication of that is that none of the calls in here are synchronous. So even if in the code you see that there is a read and there is a write, I can't assert immediately on the state. I need to wait for cluster to progress till a particular condition is fulfilled. And I mean, I can probably go inside that assert eventually. Yeah, so assert eventually you can, I mean, one of the reasons why I named the framework as tick loom is that this programmatic tick is one of the key design features of, I mean, if you see Tiger Beetle's code base, you will find exactly similar thing. Or even etcd part of it uses something like this. And what this tick is doing is that, so typically how our network software works is that you read something from the network. So whenever client sends you a message, you read something from a network, and then there is a thread of execution for handling that message that immediately picks up that and processes it, right? So if you are using thread per connection kind of a model, that's what will happen. With tick model, what we can enforce is that no processing happens unless a tick method is called on a particular object. And even if there is, because we use networked IO, non-blocking IO, you know that non-blocking IO is poll based, right? So you can poll for updates which are available on the network, and that allows you to do these kind of things. That I mean, it won't automatically start executing messages that you receive. It will do that only when you ask it to, and that makes it very easy for controlling the flow of execution, because you know that nothing is happening before the tick method is called. So you can just call, let's say, enough ticks for your nodes to, let's say, receive only a partial set of messages or do some partial set of actions. And this is a great way to simulate certain interleaving scenarios, like when when it's a multi-threaded program, when it accesses shared state, there are some random interleavings that can happen, right? I mean, this is not a multi-threaded program, by the way, but a distributed system, like we saw interleavings of reads and writes across cluster nodes, you can control a lot of scenarios like that in here. And exactly the reason why distributed systems are hard, but if you can predictably reproduce a scenario that you can spend some time trying to understand, it becomes relatively easy. Then imagine a situation where you implement something like Cassandra. In Cassandra, this scenario can happen, but you never know when that can happen. And it's just a tricky interleaving of reads and writes that this scenario will happen. And you theoretically know that, okay, in quorum-based systems, this can happen. But if someone asks you to now reproduce this on Cassandra, you can't control interleaving of messages, right? With this implementation, what you can do is you can control interleaving of messages. Yeah, So yeah, I'm open to questions, and do try out this framework.
I think I'd go so far as to say that you can't achieve determinism without having a state space.
Without having this single threaded, yeah. So there are certain design constraints that you need to put on the. There are certain design constraints that you need to have. One of them is having single threaded execution. Not doing an execution unless a tick method is forcing you to take that action.
Is there any other way that we can also enforce determinism without using
No, no, deterministically I doubt, no, because even the way Jepson tests it is, I mean, you keep it running for some time and introduce failures, and in some situations some failures might cause certain inconsistencies. You hope for that.
So in the examples that you showed,
Yeah.
that was not linearizable, right? Because
That was not, no.
for a system that supports linearizability, how would it work?
Yeah, so the system that supports linearizability will not return that. Okay, where is the? So system that supports linearizability will not return this x equal to 1 in there. So that x equal to 1 unless, sorry, or I can show it in the diagram. So this won't happen. Alice will never see value 1 unless it's guaranteed that any subsequent reader will see that value 1.
But how would that implement, like, how would the replica 3 do that?
Okay, so how replica 3 can do that, I mean, part of it is how consensus algorithms work. If whenever it sees two different values, it can say that no, I need to wait. I can't return a value. Basically, it can do at least that. But then the thing is that none of the users will get any value until this write is complete, and it's going to hamper your availability. The way consensus algorithms do that is that I mean, one of the key challenges in here is that that value x equal to 1 or x equal to 0, whatever it is, even when it's partially written, it's made available to the subsequent reads, right? Consensus algorithms do that with things similar to two-phase commit. So in transit changes, they are not made available. They are stored in a intermediate storage and only made available when it's guaranteed that it has reached majority of the replicas. And other thing that they do is also they implement this leader follower mechanism. So only leader is allowed to handle any request. So one of the problems here is that any replica is handling the requests, which give you a lot more flexibility and availability because you don't need to rely on this leader being available always.
If like replica 1 was the leader, then no matter
Even reads will go to replica 1, yeah. So none of this will then go to any other replica. I mean, even if it goes to any other replica, it will be forwarded to replica 1. And then that leader can control the sequence in which it executes the request. I mean, it can obviously execute one after the other.
so replica 2, replica 3, then it's just for failover.
Failover, yeah.
questions. Sorry, I wanted to add something actually to this. One more thing I've seen being done is if the client is topology aware, they themselves can go sort of quorum read and they can sort of do a majority of all the nodes that they know of, then try and give some. I've heard this termed as read repair. I'm curious to know if you've heard
Yeah,
of
read
this.
repair, yes. Read repair will partially fix this, but one of the issues with read repair, now with read repair, what it means is that if I know that I can't reach all three, but from one node I got value 1 and from one node I got value 0. If Alice can somehow figure out that out of this 1 and 0, 1 is the latest value, then what it can do is it doesn't return unless it again writes that 1 back to replica 2, because it now knows that replica 2 is missing this latest value. And it to some extent solves this problem, but the biggest challenge there is to figure out which out of these values is the latest. And only practical way to do that is to rely on timestamp. So what you do is, every time a value is written from that writer assigns a timestamp to the value, right? And that itself is a problem, because your system timestamp can go back. I mean, there can be lag across replicas between the clocks. Your system timestamp itself can go back in time. I mean, if it's a bad implementation, but let's say your network sync service is not working, and Cassandra has this known, I mean, not just Cassandra, but this technique of figuring out which value is the latest based on timestamp is called as last write wins based on timestamp, and it has a known failure mode where if there is a clock skew, it can very well happen that your newer value is considered the old value, just because your old value's timestamp is higher and newer value's timestamp is lower. So yeah, read repair fixes it to some extent, and consensus algorithms, what they do is they do some sort of read repair, except that they don't rely on system timestamp. So they assign a logical monotonically increasing number, which is, if you know of raft consensus algorithm, there is a concept called term or epoch. So they can assign monotonically increasing numbers to all these reads and writes that are happening, and then they can very confidently pick the latest value. I actually even have that kind of a scenario, I mean, here too.
Just wanted to add regarding this timestamp situation.
Right.
There's a very interesting paper from Facebook, I think, about designing a more accurate network protocol for the data centers, just to make the time sync across their data center computers
Yeah.
acceptable. It's incredibly detailed. It's another rabbit hole to dive into.
Yeah. So Google has this database called Spanner, which relies on Google's true time API, and the interesting thing about true time API is it doesn't give you a single clock value. It gives you a lower bound and upper bound, so it gives you a pair. The time across the cluster can be some minimum value, and maximum can be some maximum value. So time for all the nodes across the cluster is between these two, and you can utilize that then to order some of the events, but that's again very tricky. I mean, it's not very easy to. I mean, any practical thing that I have seen in practice is that kind of an API. That, like, none of the clock sync APIs guarantee that you get like a single value which is same across the cluster. Maximum what you get is the pair, like minimum this and maximum this. Even AWS nowadays has that AWS time sync service. I think they launched that. So they have a AWS time sync service and a library that gives you exactly similar kind of a pair that TrueTime gives you.
More questions? Hi.
Hi.
So, it seems that like a writer was able to write to some replica.
Yeah.
Replica. Readers were reading from other replicas. This makes you feel that it's like a leader follower kind of setup where we want other replicas to eventually get that data.
Yeah, I mean it's not exactly leader follower, but yeah, I mean
If you were
yes,
to, like,
yes.
have
So anytime you need to coordinate across replicas, it is leader follower kind of a scenario. Like even in consensus algorithms, for example, there can be tricky corner cases even if you are talking only to the leader. Because imagine that all these requests are handled by replica 1 and replica 1 you know is the leader. So write is handled by replica 1, that's fine, but reads are also handled by replica 1. But it can very well happen that replica 1 is disconnected from replica 2 and 3 for few seconds, and replica 1 still thinks that it is the leader of the cluster, while rest of the cluster has moved ahead, choosing replica 2 as the leader. And that's the reason even when you are implementing something like Raft, read requests need to be handled with special care, because one of the limitations of distributed consensus algorithms is that writes are easier to implement because they are written. There is this notion of writing something to the log, and but when you are reading, you are not writing anywhere, right? You are reading the values, and consensus and coordination for consensus, when it's based on this notion of writing to log, it's tricky to do for read requests. And you actually don't want to write while doing a read request, because if you write, then it's all fine. But you want a little more optimal solution where without writing, you still can guard against this kind of a scenario. So you will find that Raft implementations, when they need linearizable reads, they do a special handling that they don't return a request just from a leader unless that leader confirms that it itself is a leader by sending heartbeat to the set of followers. And if you see etcd code base, there is a special handling, like Raft paper documents this this kind of read, not optimization but protection against read, and etcd and similar implementations, they implement read like that.
Follow-up question over here.
Yeah.
During my study of Hasgeek, I was very impressed by how they make multi-master clusters where
Okay.
multiple nodes are of readers. Like they write in just like exact same key, and they eventually are consistent. So can you shed light on that, and what do you think about having databases like that more mainstream?
Yeah, I mean, I frankly don't know enough about multi-master, but whenever you need to reconcile between two writes which you yourself has said that they are both successful writes, so you have confirmed to your clients that both of these writes are successful, and you need to now reconcile sometime later, I haven't seen a good solution to that, because frankly there were databases like React, or even Cassandra, which implemented version vectors or vector clocks. And databases using vector clocks actually did exactly the same thing, that multiple writes to multiple nodes were accepted, resolved later. But there is no practical solution to how you resolve which write is ahead of other. And they ended up just sending both the responses to client and said, client, now you figure out which one is the latest. So I'm not sure what CodeDB does in case of multi-master.
CodeDB has a way to allow users to say that what reconciliation mechanism should be used by the master. So
Oh.
last one wins or the first one.
It again boils down to the same thing.
Code, so you can listen to the rules.
Yeah, so it's not a. Yeah, I mean, I think we have to be cautious reading database documentations, because there is an element of marketing to it. I mean, just to prove that they are doing something different than other databases. But reality is you only when you see the code.
Hey, thank you for doing this talk. So I haven't checked the framework ahead of time. So
Yeah, no, that's fine. I mean, it was not decided that I'm going to talk about this framework, so that's fine.
My question is that it's a test framework, right? So test
It's not a test framework. It's actual implementation that you can do in that framework.
okay.
Just that it allows you to write tests like this.
Right. So, okay, fine. So if it allows you to write these tests, what would be the sort of, like, where would you use these tests? For example, one way to use a framework to write tests is as a specification of behavior,
Hmm.
so as to able to ascertain what qualities does the system actually offer. to
Yes.
the platforms.
Yeah.
Is that like how one would use this, or is that one of the intended purposes?
Yes. So I mean, if you see how Jepson framework is used for testing any database in the world, you essentially keep on running various scenarios for extended period of time, and you introduce random failures, and then you get your client histories like this, and you feed it to the checkers, right? So so this allows you to do things like this as a black box of a cluster, but it also allows you to do white box testing, because you can inspect cluster state yourself.
So I think in this test, like many test frameworks and most test frameworks will focus on faults, like network partition.
Network faults and storage faults, yeah.
But one more aspect of behavior testing is, for example, different scenarios. So you mentioned MongoDB. So for
Yeah.
example, MongoDB, like if you look at this, if you look at that, if you schematic ahead of the test. Right?
Yeah.
So MongoDB has things like write concerns, which means that it allows the client to specify the level of durability. Similarly, read concerns, it allows you to specify the level of consistency. So then, would this test framework be able to factor in things like?
Yeah, I mean, you can code those kind of things in here.
Like
I mean, you not for MongoDB, but you can code it yourself. I mean, that's a yeah.
MongoDB as an example.
Yes. Yeah. I mean, you can do whatever you want.
Synchronous commit on or synchronous commit
Yeah.
off. Based on that, the test spec will differ.
Yeah.
So
Yes.
it would be.
I mean, it will allow you to do that. Yes.
Okay. So what you're saying is that I can write the test to.
You can write an implementation first and then test.
Oh, okay. So I'll have to write.
So you'll need to write implementation similar to what MongoDB might be doing.
Oh, okay.
Yeah.
Yeah. So that was my top level question. Like,
Huh.
what would be the utility? So is
Right.
this
So it allows you to write. No. It
implementation?
the implementation and then spec. Yeah. So the primary use is to actually implement stuff, and then testing is a utility around it.
When I saw the star test for Java, I thought that it's a test framework in the sense of.
No. I mean, this was just to demonstrate that the scenarios that you read in books, you can actually implement.
I mean, that would be very useful, right? Like,
Yes.
For example, Jetson. Like,
Yes.
be able to run it against systems and to assert black box
Yeah.
behavior.
Yeah.
Because, like you said, sometimes documentation is the element of.
Yes. Market. Yes. Yeah. Yes, I mean the testing side of it is simulation framework.
Yeah, and then it's
Uh,
similar to the tiger bit thing.
It's similar to the tiger bit thing. Yeah, 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 yeah.
More questions? Strongly encourage the feedback.
There's a question here.
Headphone.
So specifically to the simulation framework, so in the asserting you usually call back there was a cluster or tick method.
Yeah.
So your cluster or tick,
Yeah, I mean it is just doing tick over all the server and client nodes. Yeah.
so like so for example when we delay a particular node or
Right.
a particular replica, so what is happening is the ticks for that particular replica.
No, ticks are happening, but the simulated network won't deliver the message. So if you look at the simulated network class, right? I mean it's part of the library, but what it maintains is whenever you send a message, and I can there are certain rules that it goes through. So it won't immediately deliver it to the node where it needs to be sent. It can either drop it or it adds to a list which keeps track of delayed messages and stuff like that.
Small add-on, sir. Do you have one-way partitions in your
Yeah.
questions?
So I think you said this earlier. So I think with the tick test framework, so every object only acts on a tick.
Only acts on a tick.
That's how
Yes.
you implement, for example, tick.
Yes.
And also, I don't know if I'm using the precise term, and also synchronization. That is, or lack of synchronization, like delays, for example.
Yes.
Right? So
Everything acts on a tick.
that calculate delivery tick seems to be doing.
Yes, exactly that. So you you count ticks within a simulated network, and you deliver it not to on the next tick, but maybe whatever is the delay you have configured, you do it after that.
So that's used to basically implement those time lags.
Yes. And what that allows you to do is, if there are certain other messages that are delivered in between, like those read messages from Alice and Bob, it allows you to implement that, because you have your write messages which are in queue and not delivered on any of the ticks.
But so for these kind of things, I mean, if I were to use this word to write a test, I can simply write a test. But these are implemented.
Yeah, I mean you can write a test, but your implementation needs to support that control where it should act only on tick. So I mean you can't run it against an implementation which is already there, not using any of this.
So just curious question. Maybe
Yeah.
Outside, maybe a little bit out of context. So would there be a way to use this as a test framework, like in the sense of spec-driven design or something like?
No, as I said, I mean you first implement an algorithm and then test it, and then
But
yeah.
if an algorithm is already implemented, because I think
Yeah. I mean, this quorum replica thing or Paxos, yes, some of the which is already implemented. Then you can use to test whatever you want.
no, but like as a spec, right? Like, so I think what I have in mind is like when I say spec, it would be like a YAML based spec or a
I mean, yeah, I mean you can do that. You can add that indirection on top of this.
by
Yeah.
using an annotation processor or something.
Yeah. You can do that.
Test framework. So
Yeah.
is that something?
I mean that can be a layer that can be added on top. Yeah.
Yeah, since we're on this topic, I'll ask like, have you used model checkers and TLA plus, for example?
No, TLA plus I haven't spent much time. I mean I'm aware of it, but haven't spent much time, because I'm more interested in even you see systems which are which have TLS plus spec, but finally when they are implemented in a general purpose programming language, you will find they still are tested with Jepsen kind of tools, which execute actual production code, which might differ from what your spec says. So I was more interested in this before diving deeper into TLA plus. But yeah, I haven't.
Because I was thinking somewhat these points, right? Like if you're designing something new, and
Right.
you don't know the behavior.
Yes, yes. So if you are designing something new, I agree that you will get benefited by, yeah.
If I'm evaluating a but if I'm evaluating a given database, so I'm
Right.
evaluating a given database and I need to validate
Right.
the database
Adheres to a particular specification. Yeah, yeah. But I think Jepsen does that for you already. So Jepsen framework does that for you.
I'm not familiar with
Okay, okay. So Jepsen does exactly that. So you take an existing product and does it adhere to a particular spec or particular guarantee that
the kind of qualities that my application
yes,
needs.
yes,
Does a particular
does a particular database gives you that. Yeah, yeah, yeah. Jepsen does that for you. Okay. Yes, yes. Yeah. Yeah. Yeah, I mean, so, I'll probably share this repo because what I have, so this repo I use for conducting a workshop on flavors of consensus. So this has, basic quorum implementations, but also consensus implementations like basic Paxos, multi-Paxos, Raft. So you can refer to this to just see how different implementations can be done. Yeah.
I have a question. Could you show us some more of the Paxos log stuff? What's there?
Paxos. So actually in this, just to give background of why that Paxos log exists, basic Paxos, as described by Lamport, is a single value Paxos. So it achieves agreement on a single value. But when you need to implement actual database kind of a stuff, obviously you can't limit yourself to agreement on a single value. And you need to have agreement over a series of requests. And just following basic Paxos, essentially what this Paxos log does is, let me, is implements an ordered log of Paxos versions. So you will do Paxos for index 0, Paxos for index 1, Paxos for index 2, Paxos for index 3, so on and so forth. And essentially, because none of the practical implementations will do something like this, the practical implementations do something that is called as multi-Paxos, and essentially it looks similar. You just pull out part of that Paxos, which is one phase of that Paxos, which works for all the instances of Paxos in the log. So I mean, just to show that step by step, that how you derive Raft from single value Paxos. That's why that implementation exists, essentially. Yeah, but I will share this. I don't know where to share, but you can go to my GitHub repo. There is I can put it on the Hasgeek page. Yeah.
I was
I think this is more interesting than sharding, but yeah.
Okay, I have one question.
Okay. Last question, maybe.
Last question, then we do some announcements since there's so much tiger beetle happening.
Oh, okay.
Yeah, we can do that. So, I've had the chance to read some portions of the book. I
Okay.
sadly couldn't finish it, but what I read I really liked. Could you slightly stray from the topic? Obviously, it's really hard to write quality technical content.
Yeah.
Because there is so much of back and forth that you have to do between writing and implementing.
Yeah.
So, what was your process like in terms of striking that balance?
Yeah. I chose a easy path. I did not write before implementing stuff. So if you see, even in my book, there is a lot of reference code that's given, and the reason is that I implemented miniature versions of stuff that I was studying. I verified those implementations by talking to various people, and only after that implementation was well understood, I wrote English around that implementation. So that that was an easier path for me.
Right. Awesome. Thank you. We are done with the questions.
Yeah.
We should announce about next Saturday's.
Yeah.
Awesome. So, yeah, thank you.
Thanks.
So sorry, I haven't introduced myself yet. I'm Anirudh. I am the founder and organizer of Unmesh. It's fantastic to see all of you here. Before I go with any announcements, I would like to first thank Unmesh for doing this.
Thank you. I enjoyed the discussion.
Best thing to
It
hear.
was very random. I had not prepared any PPT as such because I did a talk yesterday and a workshop today, and I did not get a time to prepare for this meetup here. Yeah, but good discussion.
No, I think we've all had a fantastic time, and I have definitely. I came a few minutes late because of traffic, but sorry, Sarah was getting live updates and we 2 minutes about how bad it was. But yeah, I mean, even for the parts that I did get, we've covered a fantastic amount of stuff, and I just want to thank you once again for doing this.
Thank you for attending, by the way.
Yeah. It's very rare to see an author of one of the books I have on my bookshelf in person and giving a talk. So, yeah, thank you so much for that. I hope you found everything awesome.
Yeah, it was excellent.
So, yeah, just a few more announcements. I think we have snacks on the way.
Yeah, snacks are on the way, but we can have, we can
Yeah.
have a group photo also.
Yes, so a bunch of items on the agenda. We have snacks, we have small announcements. Next week on Saturday the 6th, Tiger Beetle, that is Yoranda Brief, the CEO, and Chaitanya Bhandari, who does a lot of work around Tiger Beetle's LSM and a lot of work around generally their replication and storage layers. They're coming to Bangalore as part of their 1000x World Tour, and Bengaluru Systems is very proud to announce that we are officially hosting them. So, so we have an in-person event where Yoran will be delivering his signature 1000x, the power of interfaces keynote talk. So they do a conference called Systems Distributed somewhere in Europe or in Cape Town over the last 2 years. Fantastic conference, lots of high quality speakers. Last year's conference ended with a keynote about the power of interfaces. The fascinating keynote given by Yoran. And he'll be giving that keynote again live in Bangalore on 6th. It's an HSR layout. I think the Google page is public and everyone can register. So super excited to see all of you. Hopefully all of you there. I think it'll be fun. And yeah, thank you so much for showing up today. That was the only announcement I had. So I'm super excited for that. And thank you all so much for showing up. I had a lot of fun hearing everyone's questions. I had a lot of fun hearing your going through the code and seeing your talk. So thank you so much once again. And I would like to really thank our hosts at